everyone, my name is Jiming. I'm a technical support engineer in Diana. Today I'm going to introduce you to a tutorial called Gas Explosion in the Tunnel. So in this tutorial we will simulate the scenarios where there is a gas explosion in one side of the tunnel. So before we simulate the explosion, we will first calculate what is the stress state inside the tunnel, which we take into account of the self-weight of the tunnel and also the self-weight of the sand and the hydrostatic pressure of the water above. And after accounting this static load, we apply the explosion load in time steps in the right side of the tunnel, and we calculate the stress state of the tunnel, how the principal stress changes, how the crack is forming, etc. So in this tutorial, we will split the part into a couple. So the first part is the geometry setting, which we will use the Python script provided in our tutorial folder to create the geometry directly to save time. And then we will assign the material properties for the tunnel concrete, and also the reinforcement grid, the steel, and also the thickness of the steel, the reinforcement grid, as well as the load, for example, the hydrostatic pressure load, and also the gravity of the sand, and also the explosion on the right side of the tunnel. And then we're also going to introduce you the topic of reduced geometry. In this case, we will reduce the geometry to simulate the dynamic response of the gas explosion. And for the analysis, we will do three types of analysis. The first one is the linear static analysis, which we will simulate the self weight of the tunnel and also the surrounding static load to calculate the principal stress of the tunnel to see if under this circumstance the principal stress is above the strength, compressive or tension stress of the concrete. And also we will check whether this reinforcement reach a yield stress under this circumstance. And after that, before we do the transient and nonlinear analysis, which is used to simulate the explosion process, we first do a eigenvalue analysis to see what kind of model behavior of our model, and also to calculate the damping coefficient for the concrete. So after the eigenvalue analysis, we will conduct the transient and linear analysis. We simply we simulate the explosion in a time domain, and we see how the displacement, the stress state of the concrete is developing, and also see how the crack is forming, and as well as the displacement and the acceleration on top of the tunnel. In the end, we will show you the result of these three types of analysis to see which type of analysis and which kind of a result is useful for your calculation. So without further ado, let's go into the model. So the first thing to do is to create a new project. So in this tutorial, we create a new project called gas tunnel, and then we select plane strain dimension and 100 meter model size. And in the mesh order, we select quadratic to get a more accurate crack result in the element. After the project is created, the first thing we do is to check the unit. So in this case, we only need to change the angle to a degree. And then we're done. So first part is to create a geometry, because this model contains quite a lot of operation in the geometry creation. Therefore, we use the Python script that provided in our tutorial to quickly generate the basic geometry for the later operation. And then the next thing to do is to subtract the tunnel with the opening. So we apply subtract and we get the tunnel ready already. But then we're still missing, for example, the reinforcement grid. So we will do the same by copy pasting the Python script from the tutorial here. And then we get one side of the grid is ready. You can see that all these reinforcements are relatively unorganized, so it is better to organize them based on the different geometry. So here we again use the script to categorize them into different reinforcement set, which should be representing different reinforcement thickness in the geometry. Now that we have sorted them, and then next we can just use the mirror function to create the second half of the reinforcement grid, so that they can regenerate it in the same category in the same set to reduce the workload of dragging them one by one to different the reinforcement set. Now the geometry is finished. The next thing to do is to assign material properties. So first we select the tunnel and we use a regular plane stream elements. We make a new material called concrete, and the class is concrete and masonry, and we use total string crack model. And we first activated the damping for later dynamic, and here we enter the material properties based on the tutorial. For Young's modulus and for Poisson ratio, and also the mass density, which will be used to apply gravity load. Here for we use the rotating crack model, and for the tensile behavior we select the Nodai method. Here we input the tensile strength and the fracture energy based on the tutorial. And also the residual strength and damage base. And for the compressive behavior, we select parabolic model, and we again enter the compressive strength and the fracture energy based on the tutorial. And for the damping coefficient, we first enter the number provided by tutorial, and we will later demonstrate how this number is calculated in the Diana. And now that we have the concrete material ready, the next thing is to create a geometry, simply just to define the local element axis for the concrete. Here we select it aligns with the global x direction, and we apply. The next thing to do is to assign the material for the reinforcement. We make a new material here we call reinforce, which is reinforcement material, and we select material model as for Mrs. plasticity, and also adding the damping coefficient there. And we again enter the Young's modulus and the use stress based on the tutorial. The damping coefficient is taking the same as the concrete. And next thing to do is to add the geometry, which is the thickness of the reinforcement grid. So there are different thickness, but for different reinforcement set. For the simplicity here, we will just first enter a number here, and later we use the Python script provided by the tutorial to set the geometry for all the reinforcement set. And for the other reinforcement set, we can also use the same material model. And yeah, we simply just paste the script, which can easily assign material and the geometry for different reinforcement set. Now that we have the material properties ready, the next thing to do is to assign support. So here we will assign the support only to the base edge. We make a new set called base as well. We select the edge of the base at the tunnel. We hide all the reinforcement for easy selection, and we select only the bottom edge of the tunnel, and we fix the displacement in x and y direction. And now we have the support ready. The next thing is to apply the gravity load. So here we assign a new load called self-weight, and we create a global load. We also need to take into account of hydrostatic pressure. So here it is important to introduce you the function where in Diana you can manually define the reference point for the total head to calculate, for example, the hydrostatic pressure. So here we make the y direction, the total head is 9.86 meter, so that the hydrostatic pressure will be calculated based on this level. So then we applied, for example, the pressure from the water. So we create a new case called pressure. And in this case, we will select the hydrostatic pressure. And we will select the edges on the side and also on the top as a target. And the hydrostatic head will be 10 meter. So that if add up with this 9.86 meter, then the water level will be 19.86 meter at the y coordinate. That is the water level. And then we click apply. Then you can see that the hydrostatic pressure is applied on the edges, top and the side of the tunnel. And the next thing to do is to apply the pressure from the sand on the top. Here we call it the P sand top, and we will assign it to the new load set called pressure. And we add, and here we will select only the top edges of the tunnel because they are in the relatively same y coordinate. We assign the more or less the same force, distributed force at these edges in the normal direction. And then we click apply. Great. And then we have the top pressure ready. And we will also need to apply the pressure from the side of the tunnel, the sand, because of the vertical coordinate difference in this location. Therefore, we need to create the space function to apply forces at this location. So we create the new space function called function site, and we enter the y coordinate from 0 to 7.86 meter as a factor, and then we will apply the normal distributed forces as these two sides multiplied by this space function. Here we create a new load called pressure, P sand side, and we will assign to the same pressure load case. And then we will select these two edges, and also on the right side, and the distributed forces will be -1 and times the function we just defined in the normal direction. The next thing to do is to create a transient load at the right side of the tunnel, which is due to the gas explosion. So we assigned a, for example, a new load called pressure explosion, and we will also need the new load cases. Here we call it explosion, and we will select. In this case, we will select the edges at the right side of the tunnel, surrounding the tunnel. We just select all this, and we use a distributed force as a -1 E6 in the normal direction, because we are simulating the gas explosion process, which is in the time domain. So we also need to add the time factor. Before we can do that, we first need to create a load combination. We have 4 different combinations. We need to rename them. First is self-weight, and the second one is static load, which is the pressure from the sand and the water, and the third one is explosion load, and the last one is all of the load. And then we added different load combination. For the static load, we include the pressure and the sand, and the explosion load we only include the explosion, and for all we include all the load cases. Now that we have the load combination ready, the next thing we can do is to assign the time factor for the explosion load. Here we just copy paste from the tutorial, time and the factor, and we paste it here with this button, and you can see that it's imported already here. We click OK, and now that the time factor is already applied, the next thing to do is to mesh the model. We here select the shape of the tunnel and use the element size of 0.3 meter, and we select the hex quad mesh for the model, and we just mesh it, and then we have the mesh ready. In the mesh view, you can select this option to visualize the load transfer to the mesh to check whether you assign it properly or not. Next thing to do is to set up the analysis setting. So we create a new analysis called linear static, and we right click it at the command structural linear static, which will take into account all the load combination we just defined. In the output, we can specify those outputs described in the tutorial. For example, displacement force, reaction force, external force, and yeah, you can choose all of them here. And we are also interested in the stress result. We choose principal stress, local stress, and the global stress. And we're also interested in the strain result. We select local, global, and principal again. And for element result, the result at the integration point is always more accurate, and therefore we select it in the property setting here. The same applies to other stress and strain result. Here for simplicity we will skip that part and go through the analysis. After the analysis is finished, we can check the result, for example the total displacement, and you can activate it, the mesh view, deformed or not in this menu. And we can also check the result from different load combinations, for example the result from static load and from the explosion and all. And if we look into the quasi-total stress in the maximum principal stress, you can see that the tensile strength is already greater than the tensile strength of the concrete. So before we conduct the eigenvalue analysis and the transient and linear analysis for the explosion, we first would like to reduce the geometry to save some computational time. And the justification of this application is that because we consider the bottom of the tunnel is connected to the ground, therefore it is relatively rigid, and as a result we can use a polyline to subtract or cut the model into two parts and keep only the part that is above the bottom part of the tunnel, and we conduct the eigenvalue analysis and the transient and linear analysis with the reduced geometry. So after the reduced geometry is finished, the next thing we want to do is to take into account the mass for the water and the sand on top of the tunnel. So here we create a polyline surrounding the top of the tunnel. Disable the close option, and then we assign it with a material, the distributed mass, and add a new material called mass. And we want only the mass contribution in the normal direction, therefore we input 0 here, and we input the number here calculated based on the mass, and we click apply. Because we removed the bottom part, now we have to assign the support at the bottom again. Here we select the new support, and we use the same case. We select the edges at the bottom of the tunnel, and we select the displacement constraint XY direction as well, and you check it is all assigned properly. And next thing to do is to assign the support on the side, because we assume this lateral direction has relatively confined by the surrounding sand. So we assign the support at this 2 side and we generate mesh. And if we show it again, then you can see this load is still assigned to the model. Next thing to do is to set up the eigenvalue analysis. Make a new one, rename, and then you right click add command structural eigenvalue. Here we will take into account of the gravity before we calculate the eigenvalue, and we calculate 8 eigenfrequencies of the structure, and we wanted to calculate the Rayleigh damping coefficient for the internal concrete. Therefore, we can right-click the structural eigenvalue and then add a new option, calculate the Rayleigh damping parameter. Because here we have a damping factor of 0.1, here we can enter this 2 number here, and because we have specific frequency that we want to use, and we can also enter the 2 frequency defined in the tutorial here. After the analysis is finished, you can see in the message terminal that all the eigenfrequencies that is calculated, and also the defined frequencies, and also the corresponding mass factor, and also the stiffness factor for the Rayleigh damping. And then we can input this into the material property for the dynamic analysis. In the result, you can also see the total displacement from different eigenmode. If you activated the normalized deformation, then you can see the shape more intuitively. Next, we will set up the analysis for the transient and linear analysis. Here we add a new analysis called transient and linear, and we add the command structural and linear on the right click. And then we can select the nonlinear effect, because we are simulating dynamically the deformation due to explosion, so we need to activate the transient effect. Inside the transient effect, we will need to activate the dynamic effect, and we will also need to activate the damping matrix. And in this case, because we are simulating the nonlinear effect of the internal concrete, it is also advisable to choose to update your Rayleigh damping matrix based on current stiffness and mass matrix, to take into account the nonlinear deformation of your concrete. Then we will need to assign load in the load steps. So for example, first we assign the self-weight into 2 steps, 0.5 each. And to make the result reliable, we need to select the satisfy all solution criteria, and then we add another new step called the pressure or static load, and here we will take into account of the static load again in the 2 step, 0.5 and 0.5. It makes it easier to converge sometimes. And here we need to increase the number of iteration to make the convergence. And after these 2 loads, we will activate the time load. So here we will name it explosion, and it is the time step. In this time step, we will fill in each time step and how many steps there are. And we click close. And then we also need to activate the convergence criteria. So here we set it a higher iteration number, and we select criteria as energy, and we select continue if the convergence is not reached, so that we can keep the analysis going. Again, we need to select the output for our model. So here we select, for example, again displacement, and also for example velocity, and also for other output that is specified in the tutorial. And here for stresses, we are also very interested in, for example, the principal stresses, so that we can check the tensile stress and compressive stress. And also in the strain, we can select the principal strain, and we can also select the plastic strain. For example, when the yield stress is reached in the reinforcement, then we can check it. And also we can see the crack strain. the direction of the crack opening, and also the crack width to see how much crack forming in the structure. And also for the element result, it is better to select integration point to get a better result. And then we run the analysis. The analysis will take some time, so after the analysis is finished, we can check, for example, the displacement at different load step. For example, this is the load step 4, where all the static load is already applied, as well as the gravity, and we can see the total displacement, how it's look like here. And we can also see the crack strain. So in this stage, it is already a little bit of crack opening is already forming. And we can also see the crack width of this crack is relatively small. And we can also check with the principal axis, which also represent the the tensile strength at those locations. And we can also check the reinforcement to see if any of the plastic strain is already occurred, but in this case all the reinforcement are not reaching the yield stress. At this time step, then you can see that the explosion already started. The middle pillar is already heavily deformed, so we would like to hide this to show others. After this, you can see the displacement at other location more clearly with the contour plot. And you can also see the velocity of the structure during the explosion at this time step. And now if you check the crack width again, you can see the crack already start forming at the corner of the right terminal. If you show all that at this hided location is the crack width is much dominant. And again, we hide this to keep the rest of the structure more visible. And if we keep going to even later time step, for example this one, then you can see the crack is dramatically increased at the right corner, and you can also see the displacement is very high in the top of the tunnel, as well as the velocity. The crack width is dramatically increased. It's 0.12 meter at the top right corner. If you go one further, the crack is even more on the top of the tunnel, and the top of the deformation is already reaching 0.39. The velocity is also very high. The crack width is still around 0.15 meter. You can also check the axial force, axial stress, and reinforcement. You can see that the reinforcement in the middle is already greatly deformed, as well as the strain. Then you can also, in this case, you can also check the plastic strain because the deformation is so large, especially on the top of the tunnel. And if you select one node on the top, then you can plot, for example, the deformation with the time step in the vertical direction. And here we select the time step. You can see the displacement is increased with the time step. And for the velocity, it starts to increase and then slowly getting back to 0. That's all for the tutorial. If you want to try it yourself, you can find it in the Diana website. You can go to the tutorials in the dynamics. If you go below, you can find the tutorial we explained today here. And you can also find the Python script in this folder, in your Diana folder. Thank you very much for your attention, and see you next time.